will be telling you about strongly cospectral vertices and Cayley graphs, and actually not so many other things. Mostly the strongly cospectral vertices and Cayley graphs. Let me see. I lost my pointer somewhere. Oh, there it is. Okay. So I'm going to start with some basic definitions. I'm going to define strongly cospectral vertices and Cayley graphs. And then I want to just quickly go over some fun facts about Cayley graphs and sort of the reasons for why I really like working with Cayley graphs. And then, so the sort of the result I'm presenting in this talk is a bound on the number of strongly cospectral vertices, or the number of pairwise strongly cospectral vertices that we can have in a graph. And the way that I took to get there was to first sort of find a connection between the multiplicities of the eigenvalues of the graph and the number of pairwise strongly cospectral vertices that it can have. And so we're going to look at that. And then finally, so going from there, that of course doesn't tell us anything unless we know anything about the multiplicities of the eigenvalues. And so in general, for these graphs I'm going to be talking about, we don't know very much. So for Cayley graphs in general, or I don't know very much about those, but we can say a lot about the multiplicities of a cubelike graph. And so I will be sort of talking about that in particular. And so here is a picture of a graph. And right now I'm not really going to explain what it is, or not really going to talk about this graph, but I will tell you why it's there. And so when I was an undergrad in math here at the University of Iceland, then I had a professor who was a particularly good lecturer, and he had this technique where he whenever he noticed that sort of he didn't really have our attention anymore, which tended to happen every now and then, during his lectures in Calculus 2 or something. Then he would just stop the lecture. He would just walk away from the board and face us and tell us a story about another professor at the department, always the same one. And we of course would all wake up, and then he just kept teaching. Now I don't have any stories, and I'm not a very good storyteller, but what I do have is a large collection of graphs that look kind of cool, and I'm hoping that they will sort of catch your attention if in case it happens that you might sort of have lost track of what's happening, which tends to happen to me during talks. Maybe not everyone has my attention span, but and also what's good about this is that they are not entirely unrelated to this talk as well. So I'll come to it. I'll come back to it later, actually. But so let's just go to some basic definitions. So we let X be a graph with adjacency matrix A, and we say that vertices U and V are strongly cospectral in the graph if for each spectral idempotent ER of A, we have that ER EU is equal to plus or minus ER EV, where so the capital ERs are the spectral idempotents of the adjacency matrix, and EU and EV are the standard basis vectors indexed by U and V respectively. And so this is sort of a standard definition of vertices being strongly cospectral, but I'm not going to be very concerned about this definition because we have a sort of a characterization of strongly cospectral vertices in Cayley graphs of abelian groups. And so that's really what I'm going to be using, or what I have been using as my definition, working only with these graphs. So I'll define a Cayley graph next. We let G be a group, and we take an inverse closed subset of G that doesn't contain the identity. And then the Cayley graph of G with respect to this set C, which we call the connection set, has the group elements as its vertices, and then two vertices G and H are adjacent if HG inverse is an element of our connection set. And then in particular, a Cayley graph of abelian group, we will call a translation graph. And this is what we are concerned with today. And then we talk about circulants as Cayley graphs of cyclic groups, and cubelike graphs as Cayley graphs of the elementary abelian two groups. And so first thing to just quickly note about Cayley graphs is that they have a lot of, obviously they have a lot of nice structure, and sort of what we want when we make a connection between two different types of math, then we want, of course, what we want to be able to do is that we want to be able to use some group theory to tell us something about the graph theory and vice versa. And this is certainly true for Cayley graphs. And Cayley graphs in particular, they are vertex transitive graphs, which makes them sort of nice and just cute, and it is important for what we will be doing. And so finally, I'll define characters, and I'm going to define a character of an abelian group as a homomorphism from the group to the multiplicative group of the complex numbers. And for those of you who are familiar with representation theory, this does coincide, this definition coincides with irreducible characters of representations of abelian groups. But in general, for non-abelian groups, the characters are not homomorphisms. They are only for abelian groups. But it's nice to be able to just define them like this, because we're only going to be talking about abelian groups. And then also what's important is that the characters of an abelian group form a group under pointwise multiplication, and that this group is isomorphic to our original group. Okay, so here we have another graph. This one I really like. It's very cute. There's a lot of concentric circles. Just, you know, like that one. So let's talk about some nice properties of Cayley graphs and translation graphs, actually, in particular. So if X is a translation graph of a group G with the connection set C, then the characters of G are the eigenvectors of our adjacency matrix, the adjacency matrix of X, and then the eigenvalue corresponding to an eigenvector chi is what we call chi of C, and which is just the sum of the values of the characters over the connection set. And we are thinking of now, we define the characters to be functions on our group, but we can also think of them as vectors that are indexed by the group elements. So they're just vectors living in this vector space, which is indexed by the group elements, where our adjacency matrix, that's a space that the adjacency matrix is acting on, because that is indexed by the vertices of the graph, which are the group elements in a Cayley graph. And so one thing that's really nice about this fact is that each group has a lot of different Cayley graphs. You can choose different connection sets and we get different non-isomorphic graphs, but all of them are going to have the same set of eigenvectors if we fix the group. But their eigenvalues can be different, because those are the eigenvalues are dependent on the connection set, and the eigenvectors are not, which is kind of nice. And so, sort of coming from this fact about the eigenvectors, we have this lemma that's currently you can find it in unpublished notes by Chris and Gabriel. That if X is a translation graph, then a vertex G is strongly cospectral to 0, if and only if both of the following hold. But G has to have order at most 2 in G. And if C and Phi are characters that have the same eigenvalue, then C of G is equal to Phi of G. So, okay, firstly, because we are talking about abelian groups in this talk, I'm thinking of them as additive. So it's a good thing to mention maybe. So I do have a 0 in my group. And also now, because our graph is transitive, vertex transitive, then it is sufficient to only consider what is happening around 0. So when I say that vertex G is strongly cospectral to 0, this is a characterization of all the strong cospectrality that's happening in our graph. And so the first condition here already tells us a lot. It is a restriction, because a vertex that's strongly cospectral to 0 has to have order 2. So in particular, a translation graph for a group of odd order has no strongly cospectral vertices, because it has no elements of order 2. This sort of immediately follows. And then sort of similarly, a circulant has at most 1 vertex that is strongly cospectral to 0, because a circulant has at most 1 element of order 2. And the same thing happens in any graph, any translation graph, where the group has a cyclic Silo2 subgroup. So that's exactly what it means. It just has exactly 1 element of order 2. So this is the only one that can be strongly cospectral to 0. And then this is, of course, what we really want when we have some set of things in a group that contains the identity, that the set of vertices that are strongly cospectral to 0, they form a subgroup of G. And again, because these elements all have to have order 2, this is an elementary abelian 2 group. Okay, so I wanted to just ask for questions quickly, if there are any. Okay. So, specifically, Cubelet graphs, we have this simple condition that that an element in a group has to have order 2 when it is strongly cospectral to 0. Then what happens in cube-like graphs where all the elements have order 2? The question here is could all the elements in the group be strongly cospectral to 0 because they all have order 2? And the answer to this question is no, they cannot. But this is sort of a bit harder to see than what we've noted about the cyclic groups, for example. And so I came up with this lemma here that when we have a translation graph, and this holds for all translation graphs, we let H be the subgroup of G that consists of the vertices that are strongly cospectral to 0 in X. And then we let L be the index of H in G. Then the multiplicities of our eigenvalues are a lower bound on this index on the subgroup. So if we have large multiplicities, the index of the subgroup has to be large, which means that the group itself has to be small. So then we have not very many pairwise strongly cospectral vertices. And this lemma I'm actually going to prove if the technology allows me to do so. So recall that if we have two characters with the same eigenvalue, then they take the same value in any vertex that is strongly cospectral to 0. So if we have two characters corresponding to the same eigenvalue, then they take the same value in all the elements in H. H is our subgroup that consists of the elements that are strongly cospectral to 0. Okay, so we're going to consider the quotient group of G by H. We defined L to be the index of H and G, which equivalently is the order of this group. And now remember that the characters of an abelian group they form a group, and this group is isomorphic to our original group. So this quotient group has exactly L characters. Okay, there are as many characters as elements in the group. And so I'm going to define the lift of a character of a quotient group to G. Given a character phi tilde of the quotient group, so we define chi. We define chi, a function from G to the multiplicative group of the complex numbers, by letting chi of x be equal to chi tilde of the causative H containing x for all x in G. And this is in fact a character, which I'm just going to claim. It's not too hard to see actually. It's called the lift of chi tilde to G, and it is pretty clear that H is contained in the kernel of chi. Because in our quotient group, H is the identity. So chi tilde, which is a homomorphism, maps it to 1. And so chi maps every element in H to 1. Okay. So now I'm going to state this fact here. This is a well-known result from representation theory. If you want to see a proof of it, you can look up any book on representation theory of finite groups. That if we associate each character of the quotient group with its lift, then this is a bijection between the characters of the quotient group and the characters of G that contain H in its kernel. Okay, so we saw that we can take a character of the quotient group and get a character of G which has H in its kernel, but this is in fact a bijection. And so again, we have exactly L characters of the quotient group, and so this gives exactly L characters of G that have H in the kernel. Okay, so now we'll let theta be an eigenvalue. So theta is an eigenvalue, and we take all the characters or eigenvectors that have this eigenvalue, and we call them C1 up to Cm. And then theta has multiplicity n. And so we want to show now that m is less than or equal to L. Okay. So for each I, let's define a new character. Actually, we define this function. I already spoiled it, that it's going to be a character. We define this function chi I by letting chi I of x be C1 of x times Ci inverse of x where we define this inverse to be just a pointwise inverse. So we're just taking the inverse of each value of Ci of x. And with this definition, we remember that our characters, they form a group. And this is the multiplication in the group. And so, which means, firstly, that Ci inverse exists. Ci is a group element and it has an inverse, which is exactly this inverse. And it also means that Ki is in the group. So it is a character of G, because it's just the product of two characters. Okay. And we can pretty clearly see as well that the Ci, if we have two different, if we have Ci and Cj that are distinct, then these give distinct Ki and Kj, just by definition. And then, because C1 and Ci, they take the same value on each element of H, then we can see that H is in fact contained in the kernel of Ki. And what we have done now is that we have taken our m characters or eigenvectors that for this particular eigenvalue. So they give us the multiplicity m, and then we have mapped them bijectively to m characters of G that contain H in its kernel, but they're at most, actually they're exactly L of those characters. And so M has to be less than or equal to L. And that is the proof. So do we have any questions? Okay. So we have now founded the index of this this subgroup below by the multiplicities of our eigenvalues. And then what we want to do next is what do we know about the multiplicities of these eigenvalues? And like I said before, in general, with translation graphs, I don't really know much about them, but there are some things that we can say about cubelike graphs in particular. And so now remember that that each eigenvalue of a translation graph is given by the sum of the values of the characters over our connection set. And then in a cubelike graph, all the elements have order 2. So in an elementary abelian group, all the elements have order 2. And which means that mapping them with the homomorphism into the multiplicative group of the complex numbers, you have to take value either plus or minus 1. The characters take values plus or minus 1, and then the eigenvalues are just sums of some collection of these character values. So they're just sums of plus and minus 1s over the connection set. And so it follows that the eigenvalues of the Cubelet graph are integers, and they have the same parity as the degree of the graph, which is equal to the size of the connection set. And they also because our degree, the degree of the graph of a regular graph is equal to the spectral radius, meaning that we have these integer eigenvalues and they lie on this interval from n to minus n. And they're all either all odd or all even. And so we already have some restrictions on these eigenvalues. And then furthermore, we have this sort of fact, or it's better to call it a claim, that the spectrum of a cubelike graph, it kind of looks normally distributed, which of course doesn't really mean anything on its own. But what does happen is that we have this interval, and the eigenvalues that are close to n or minus n, they have low multiplicities, and then the eigenvalues that are close to 0 will have high multiplicities. So this claim on its own doesn't really help unless you sort of define what you mean by this. But you don't really need for what I want to do. The only thing we need is that we need one eigenvalue with large multiplicity. And so this is what I came up with. So if X is a cube-like graph on 2 to the d vertices, where d is at least 3, and k is equal to half d, then it has an eigenvalue with multiplicity larger than 2 to the k. I'm not going to prove this because it's not elegant in any way, and not appropriate for a talk. But pretty much when we have this lemma here and the one before, this theorem here follows from the two. That a cube-like graph on 2 to the d vertices, where d is at least 3, it has at most this many pairwise strongly cospectral vertices. So if d is even, we get at most 2 to the half d minus 1. And if d is odd, we get at most 2 to the d minus 1 over 2. Pairwise strongly cospectral vertices. And it's sort of worth noting that this actually doesn't hold for d to 1 or 2, because this bound would give us 1, whereas both K2 and C4 have a pair of strongly cospectral vertices. And so the question that we of course want to ask at this point is whether the bound is tight. And as I said, it doesn't actually hold for d to 1 or 2, but so for 3 or 4, we are looking for a pair of strongly cospectral vertices, and this happens in most cube-like graphs. Most cube-like graphs actually have perfect state transfer, which is sufficient for the vertices to be strongly cospectral. So there are a lot of examples, but we have, for example, the hypercubes. Then we have the antipodal vertices that are strongly cospectral. And then for d equal to 5, this is sort of where all of this, or this project that I've been working on started, where I started looking for sets of strongly cospectral vertices that are larger than just 2. And I started looking at the Cubelet graphs on 32 vertices, so 2 to the 5. And I actually started it because back when we still had these seminars in person, once after a seminar, I was talking to Ada and Harmony and Xiaohong, and I think Ada asked this question of whether we do get examples of actually, she was thinking about whether we do get examples of strongly cospectral vertices in Cubelet graphs that do not have perfect state transfer between each other. And one way to address this question is, well, if we have large sets of vertices that are all pairwise strongly cospectral, then this is going to happen because we can only have perfect state transfer between a pair of vertices, because that is monogamous. But if we have a set of 4 vertices that are all pairwise strongly cospectral, then we might have pairs there that have perfect state transfer, but we're also going to have some pairs that are strongly cospectral but don't have perfect state transfer. And so that's why I started looking at these. And I started just running through all of the graphs on 32 vertices, and we in fact have exactly these 6 graphs and their complements that have a set of 4 pairwise strongly cospectral ones. And so I don't know if you can see it properly, but some of the vertices there are colored. There are 2 red ones and 2 green ones. And the red ones are the 0, and then the vertex it has perfect state transfer with. And then the green ones are also strongly cospectral to 0. So the colored vertices are a set of pairwise strongly cospectral ones. And out of all the Cubelet graphs on 32 vertices, these are the only ones that have this property, these and their complements. And then I was curious of what happened on the Cubelet graphs on 64 vertices. At this point, I hadn't actually proved my bound, so I thought that maybe we would get bigger sets of strongly cospectral ones. I was actually looking for a set of 8 on the 64s. And I also want to mention that I got a list of these graphs from Gordon Royal, which if I hadn't, then I probably wouldn't have started this, because there are already a few 100 million Cubelet graphs up to isomorphism on 64 vertices. And I don't think I would have started generating those by myself. So that was really cool. And certainly there are a bunch of those that have a set of 4 strongly cospectral ones, and you've been seeing them before as well. There are actually quite many. I have this picture. I don't think I have more pictures, but I'll only show them if I'm asked. But there are quite a lot of examples. And then, so we get to dimension 7, and we are now looking for a set of 8 pairwise strongly cospectral vertices for d equal to 7 and 8. And I actually have no idea if those exist. I am looking for them, and I've been looking for a while, and I'm not finding any, and I want to believe they exist. I want to actually believe that the bound is tight for all the, and that it could be proved by construction, only because I have no idea how to prove a better bound if it's not tight. So I'm hoping to find some more graphs that would give me insight of how to construct maybe a general connection set for all dimensions. But so far I haven't been able to do this. And so that is the end of that. Thank you.
All right, thank you, Sophia. Do people have questions for Sophia? You can either unmute yourself and ask or type in the chat. Maybe I'll start. So I guess this might be sort of moot because I don't think lemma 1 will work for anything when you move to non-abelian groups. But I'm wondering, I know that like you can still lift characters in like in a good way for non-abelian groups. So I'm wondering if you can preserve much of lemma 2 in that sort of general setting.
Yeah, I mean, that's a great question. So lemma 1 actually, it doesn't generalize to non-abelian graphs, but it does, but I should have looked into this better, but you can still say some things about, well, actually, just because this fact here doesn't hold for non-abelian groups. But if you have normal Cayley graphs, so Cayley graphs where the connection set is a union of conjugacy classes, it's closed under conjugation, then we still have some. I think we still have some nice way to sort of to find the eigenvalues, like the linear characters, the characters of dimension 1, they're still going to be our eigenvectors, and then you have some more eigenvectors, and I think they're somehow related to your other characters. I'm not completely sure actually, but so but yes, for sure. So you can, whenever you have a normal subgroup, you can lift its characters to the original group, right? In this same way.
But it's just not going to give you cospectrality information, I guess, because lemma 1 doesn't hold.
Right. Yeah. No, actually, yeah. I still suspect that the strongly cospectral vertices are going to form a subgroup in a normal Cayley graph. I'm not completely sure, but I hope so. That would be nice.
Cool.